All right. On the group allocation, after the class, I'll go back. Then I was just preparing them and I will put them. Some of the files with the group names you have sent, they have extension tx like text file. And those files seem to be infected with virus. So I'm not able to open them. So please send those things, send those files, those of you. Either you can copy it in the email or send it in a MS Word or Excel file. Some of you have not got any group yet. So some of you have requested me to put your names in some groups. And I have tried to compile some of those names. If I have missed somebody, please remind me again. So today, we will start with a new topic called co-integration. It's all there in the blackboard. So let's try to understand what it is before. We study non-stationarity. In that context, we tested for unit using a variety of procedures. How many of them you know? So how many test procedures we have used to test for unit 2? So starting with augmented decoupler, then its extension with respect to GLS transformation, autocorrelation, structural break, asymmetric information, all those things. So 3-4 different types of unit group test we have done. Now we will use that knowledge. So we will use our knowledge of unit test and the characteristics of non-stationary dynamics. To study a new topic. And basically, this is a multivariate extension of joint modeling of non-stationary dynamics. So far you have done everything in the univariate context. Means one time series. Whether a time series is stationary or non-stationary, testing for non-stationarity of the time series using unit procedures, that is what we have done. Now if we have several series, we'll start with 2, but if we have several series which are non-stationary, and then what shall we do? So how to model them jointly? If they are non-stationary together, how to make them stationary, how to study their dynamic behavior. So that will be the context of all. So it's basically, so we are moving from univariate to multivariate context. In this case, our idea is to check the non-stationarity of series together and model their joint behavior. What we call co-integration. So this is what modeling their joint behavior. We call them co-integration. So co means together. So co represents that is the idea. Okay, so if we have two or more series which are non-stationary in nature, so we will see how they move together in the long run, and still they make a very stable long-term relationship. Let's have some examples for the real world. Some questions. Are you able to see what I'm writing, or shall I make it a little louder? Is it okay? Quite bad with this MS Word. I never use it. Take my experience in this case. Well, a couple of questions. Think about two terrorists put into a prison cell, and the prisoner, the jailer, asked him, form a long-term relationship, stable. I'm sure if they have some ego problems, you might have heard in numerous jails across the world, so they find one of the bosses being killed. So you hardly see if there are two non-stationary series, unless we do something, so either one of them will kill each other, or if they combine together, it will be chaos for the world. You know that. Similarly, if we put two saintly individuals, like Pope Francis and somebody from Indian saint together, they will meditate and form a very long-term relationship. Third, very interesting question. Although you are yet to experience this, some of you, I guess, two individuals, they marry, and you know, you do not why know it. At the initial stages of your married life, everything is so rosy, very nice. And then after some years, then you feel like Well, you feel like like we fight. It's common. Yeah, we do. So, but we still, people live for 50 years, 60 years. One of the famous econometricians, Clive Granger, who won Nobel Prize in Economics in 1994. So he was married for 54 years. Then he died. And this co-integration technique that I'm going to teach you, it is his invention. And for which he got the Nobel Prize. It's an extremely important technique to understand the co-evolutionary pattern of any economic or financial time series. So he asked, actually he was a professor. Let me give you a little background. He was a professor of econometrics in Birmingham. And long before 1984, when he invented this technique, and so a lot of people were doing all these univariate time series, like non-stationarity, unit put, etc. Then Professor David Henry from Oxford, he is also a very big econometrician, and then once they had a discussion, then he asked, what will happen if we have two or more non-stationary time series in the same kind of system? Like in a macroeconomic system, we have inflation, we have GDP, we have money supply, interest rate. In a financial system, is stock price, future prices, like all these things. So if we find within a specific system, there are two or more non-stationary, unstable series, can we still expect a long-term stable relationship between or among them? So that was a question which Clive Granger liked the most. Then he thought, let me think about my own life. I always fight with my wife, but we are still living for 55 decades together. So how did it happen? So he started thinking about this question. And then on his flight from Birmingham, and he used to also teach in Los Angeles, California, Los Angeles. So on his flight, he thought about the econometric method which could actually form the basis of co-integration. Then when he reached there after a year, he wrote a paper on co-integration. And that became a famous paper, that one that I'm going to teach you, and based on which hundreds of very tactical, financial, practical, and very theoretical papers have been written based on which. So that he became extremely popular among practitioners of finance and economics. But in this case, so love is something within a marriage. Love is something, even if you have differences on everyday life, but still it can bind two people together. I give you an example here. You might have seen from my lecture note. This is something I have copied from a movie called Forrest Gump. Forrest Gump, you might have heard about that movie. And the Forrest Gump himself, it's an Oscar-winning movie. I like that movie. He keeps on running. And there was a typical conversation between Forrest Gump and Jenny Coran, that is his girlfriend. And so Forrest Gump asks, will you marry me? Jenny turns and looks at him and says, I would make a good husband. Jenny said, you would, Forrest. Forrest Gump says, but you won't marry me. Sadly, you don't want to marry me. Forrest Gump, why don't you love me, Jenny? Jenny says, nothing, Forrest Gump. I am not a smart man, but I know what love is. So that he gives an indication. Despite all the imperfections we have among ourselves, I can still make a good husband because of the concept of love. So that is a binding force that can make two non-stationary series unstable relationships stable. Exactly, you see, all these econometrics or statistical techniques, those have been invented. Those were firstly conceived of philosophical stuff. It is just not that I was just working with non-stationary series. I just wrote down some equations, it became co-integration. No, not like that. Just take into account Granger's own admission that he invented co-integration looking at his own marriage life. That is how we do. Always try to think that equations are not important. All mathematical stuff, I know many of you like just derivations, problems, solutions, and I have seen that sometimes whenever I am not going through systematically my lecture notes, page after page, you still have some trouble. But I do not like that one. Sometimes I go take into account some one page here, then I go back to my some lecture notes, then start deriving. But some of you have you accustom your mind in such a way, you just go page by page, this equation explanation, this equation explanation. But that is not the way it should be. Try to understand things philosophically. If I am trying to say something, or there are some econometric equations written somewhere, so think that somebody might have thought large about it. Very, very good thinking must have gone behind it. So all these equations, try to take them in a, not in a mathematical form, but in a language form. So co-integration basically is co-integration unit root, and I have tried to explain those things to you, that these are basically philosophical stuff, but those philosophies which have been mathematically modeled to give some kind of practical implications, and we are using them in hundreds of thousands of different cases. So co-integration also exactly has the same problem. So whenever you see a textbook, you see all those equations, try to understand what is behind the equation. So as long as you have understood the story behind the equation, then these equations, mathematical stuff, they are just simple stuff. If you are good at deriving, that won't be a problem for you. But what will be most difficult for you is to understand the reason, how it has been formed, what are the meanings of those things. These are extremely important for you. In the exam or in the assignment that I have given, if I get some proof of your understanding, that you have showed some exceptional skills in illustrating or explaining things, not just the equation. I like equation. I'm a mathematician myself. I'm an econometrician myself. I did PhD in econometrics. If I just want, I can come here, put those equations and go back explaining. So that's easier for me. But remember that as a teacher, it's a very, very difficult job for me to make econometrics or statistical concepts look like a lie. It's extremely difficult. So that's why you see I jump around, try to explain things in a different way, make humor. Why I do so? Because I try to put some life into the mathematical concepts. Because at the end of the day, I am sure after you pass your MSc, are you going to use co-integration or this unit stuff in anywhere in your life? No. But I'm sure if I have told something interesting, that you might carry. And of course, if you are in academics or in some research houses, obviously you will apply them, that's for sure. But otherwise, what you will take from these classes? The basic philosophy. That is most important. So, the idea of telling you this story is this, that if we have two or more non-stationary, unstable states, the world does not collapse around you, we can still make some kind of stable relationship. But there are some mechanisms involved. And that mechanism I am going to now explain to you. So that technique is called co-integration. Okay? So we have in the Blackboard two different lecture notes. One is the PowerPoint file explaining the techniques, another is PDF file. So in the PDF file, it should look something like this. Let me see if I have here. So that type of thing, co-integration application, that one is there. It is in the Blackboard. What I will try to do, the PowerPoint file that you have, it is for your reference. There are numerous applications, little bit of tough mathematical formula, explanations are there. I will explain everything. But let me start with a simple application of co-integration. And then I move on to explaining the procedures of angle gradient procedure to bivariate, multivariate. I will explain everything. So this is the file that is also available in the Blackboard. And then you have this PowerPoint file. So we'll use both of them. Okay? Now, let me try to start with the most technical description of what we call a co-integration. So let's think about that we have a variable called x, and we have a number of variables xi, and observe over time period t. So here I can be 1 to n, so we have a variable x. So we have a variable x and I represent 1 to say n. Observe over time t, so t also 1 to t. And in this case, at least if I at least 2. So whenever we used to do that, for unit root case, you did only xt, only one series. So we try to introduce more than 2 or more. Okay, so I t, and I'm assuming that this is distributed error. This sign is called distributed, and I d I. So once again, let me remove this I here, I here. So this xt is distributed of integration of order d. Okay, so what we call this integration of order d. Integration, what is called I, and or order, then d, where d can be in this case equal to 0 or d can be equal to 1. So when d equal to 0, we have stationary, and I have explained about these concepts in my first 2-3 lectures when I was discussing about trend, seasonality, then ARMA processes. I was explaining that. So this is d equal to 0 stationarity, d equal to 1 unit root. Okay. But there are in between cases, d equal to 0, d equal to greater than 0, but less than 1. So those cases we will not discuss at least during the lectures, but at least you should know d lies between 0 and 1. So that is what we call long memory process. We will not discuss about that, but remember this is a possibility. Long memory process. We are only concerned with these two extremes, d equal to 0, d equal to 1. So when d equal to 1, so xt, any univariate time series, so is I1. So when I say I1, it's just like a unit process, integrated of order 1. And when this is 0, I0 process, so that becomes a stationary process. And when it is I1, so it's a non-stationary or unit process. So these are the two things. This is how we describe.
What if it's 0.4? What do you do?
Sorry?
If it's 0.4, what happens?
Very good. And then we call it a long memory process. Like, or what we call fractional integration. Integration of order d, that's a fractional parameter. But you might be wondering what are the differences there. Okay? You can illustrate this one using one simple example. Say this is your lag length. And then what we call here ACF, autocorrelation function. So autocorrelation means that successive lag dependence of an observation. So in this case, let's say xt, xt minus 1, xt minus 1, xt minus 2. Likewise, if we have, say, p lag length, so a relationship between xt, t minus 1, t minus 2, t minus 3 until t minus p. So that's a correlation. So let's say we have here P lag and P is greater than 1. So let's say P is 50, 60, 100, 20, 30, anything, any number. Now, let's say we have likewise think about this graph. I join all the, so the lag 1, 2, 3, 4, 5, 6, likewise for a long time period. The correlation coefficient at the first lag, the correlation is very high. Second lag, the correlation is smaller, then smaller, then smaller. It declines over time. Why does it so?
Past observations affect, like, the further we go to the past, the less these observations affect.
Now that's a very good point. Now you can see, okay, so you see the idea. The idea is that whatever happened, say 20 years ago, some shock, something happened. So we are assuming, under the assumption of normality, as long as we are rational, normal individuals. So whatever happened 20 years ago should have less influence on our life today than something that happened 5 years ago, 2 years ago.
Yes, sir.
Exactly. So that is what a philosophical thing. So see how we translate. So correlation, when I say declining correlation, so the idea is this. So where a correlation, autocorrelation function is, say for example, just like this. So after 3 lakhs, 4 lakhs. So whatever happened 5, 7 years ago doesn't matter to me. Only yesterday, day before yesterday, or even the previous, like after 3 periods, stationary series. Okay? So here, in this case, D can be something here. So if for this one, so D can be somewhere near 0. And here, you see, it is declining, then asymptotically over time. So maybe 100 years ago, 50 years ago, something happened. I still see the influence. So that type of agent, we can say, it may not be rational enough. Okay, so, or even if the agent is rational, but the system may be extremely imperfect market structure, incomplete information, some degrees of irrationalities can give rise to the graph. That means something happened a long time ago, but it still influences. And there is no way, there is no opportunity to see it is just going on forever and forever. So there is, I don't see any possibility of convergence. So in this case, I can say D equal to 1. Unit root series are random one, where the both mean and variances, they always expand over time.
So if it's asymptotic to the horizontal,
Exactly.
D equals 1?
D equals 1. But now coming back to your question, you say whether if D equal to 0.4. And so 0.4, if we go by the convention of distinction between I0 and I1, so this D equal to 0.4 that you said, so that's a recent invention. Once again, made by Clive Dillinger. That is what he invented, something fractional integration. He questioned this 9-phase assumption. In the real world, you will never find a person who is extremely stable, or you will not find a chaotical. Well, I am not talking about the terrorist, that's a different story. But we are normal human beings, so I cannot find somebody who is extremely I1. So these are possibilities, practical possibilities, yeah, theoretical possibilities. But most of us are somewhere in between. So here, for example, you can be an I 0.4, very nice gentleman. I can be somewhere 0.7. I'm not very chaotic, but somewhere 0.7. Sometimes stable, sometimes not. 0.7. So we can distinguish individuals, financial, economic time series according to the degree of integration. That's fractional or flexible enough, most generalistic in nature. So in that case, it may be the case, it's just like that, maybe after 50 years. So it takes long time for an economic time series, a shock to an economic or financial time series to take around. And I always give this example to every class. Whenever I come, I think it's fine, it's very interesting. I ask this gentleman to slap me, and so that if I am a good person and a forgiving person, so I forgive and forget. So I am stationary. And if I am a united person, so after 50 years or so, I see you on the road and I slap you back. But if I am a long memory, somehow say 0.4 according to you, and then I carry this feeling for 3, 4 years, 5 years, then I already had in mind that whenever I see him, I slap him back. So after 4 years, I don't see you, just 7, 8, 9 years old, forget. Okay? But I am near to 0.89, or somehow or rather, I will take some revenge. Even though I will not slap you back, somehow I will fail you in my class. I can do that.
That's why I'm not slapping you.
You see, my friend, you are very clever, but I am a good man. Well, I don't claim to be one, but at least I am rational in that extent. Anyway, but philosophically speaking, that is the idea. Okay? So wherever you are, whether you are ID, so D can be between 0 and 1, 0.4. Statistically speaking, there are some ways that if a time series statistically if D is less than or equal to half, this is what we statistically say covariant stationary. Okay? Something very close to stationary series. But D is greater than half, but less than or equal to 1. So that's both of them what we call long memory. Long memory. But in this case, I call it a stationary long memory. I carry some source by forward. And in this case, I call it non-stationary long memory. These words or concepts have been developed by looking at the statistical properties like autocorrelation function, the behavior of autocorrelation function when the order of integration of a time series is greater than 0.5. But it can be equal to or less than 1. So these are what we call non-stationary long memory. But if something is, so let's say, forget about less than 1, something 0.9, 0.89, like that, near unit processor. And whenever we have D equal to or greater than 1, you know what happens. Unit processors, completely lost. Unpredictable, volatile. You can never predict those kind of things. Okay? So this is what we call half stationary long memory, greater than half, less than 1, non-stationary long memory. And like this here, at some point of time, maybe it will take 50 years, 60 years, but there will be some kind of convergence. And when it is equal to, greater than equal to 1, no possibility of convergence to the mean. Okay? So this is what is the concept of integration. So while I am teaching you co-integration, first of all, there are two words of co-integration here. One is co-integration with I1 variables. Okay? So co-integration theory has been developed in two strands. Co-integration, one is with I1 variables and distinguish it between I1 and I0. Okay? This is one class. Second is ID, where D is less than 1 and greater than 3. Fractional. So this is what we call fractional integration, fractional co-integration, which you will not be taught, my friend. I don't want to trouble you. Yes, if you have some interest, you should. But what I will try to tell you is extreme, knife edge cases. So that you understand those things, then these things, fractional co-integration, this type of thing requires some knowledge of statistics, which you call it the fractional spectral analysis. Have you heard about them? Spectral analysis, like frequency domain, like sine, cos, theta, those kind of tan, so those kind of things like, very, very minute frequencies of time series, mostly applied in rocket science, engineering. Okay, so fractional integration with spectral analysis of frequency domain are basically those kind of things. Extremely sensitive shocks affecting the behavior of any economic or financial time series. So that is a different one. I will only teach concentrate on I1 and I0 basis. Okay, so let me begin with this one. Then when I was discussing about this characterization of x variable with ID, so in this case, I mean it should be I1. So I discussed about only one time series. So if I have several, now if x1 is I1, x2 is I1, x3 is something else, so how can we put them together and model them? So if say x1 is I1, x2 is also I1, then how to model them? So that is our question. Of course, we can have a different question. If x1 is I1, but x2 is I0, it is also possible. x1 is 0.5 and I 0.5 and x2 is I 0.9. Order of integrations are different. So we can have several possibilities, but the simplest possibilities are that either both of them are stationary or both of them are I1 unit-root processes. So in that case, how to study their joint behavior, how to model them, how to test them. So that should be our idea. Okay, so one of the theorems that says now, if xit is distributed as idi, so di means d1, d2, d3, x1 is id1, say 0.4, x2 is 0.2, say 0.5, likewise, differential degrees of integration. Then, whenever you have a z variable in sum of those things, what? So it should be alpha I, xit, sum of them, I equal to 1 to k, means k number of variables you have. 5, 6, 7, 8. We say, I gave you assignment. I have given you, say, some data. You will see. You might have seen data 1, XLS 2, 3. So 3, 4 variables I have put together. So let's say we have 5 variables. And so k equal to 5. And say you have employment, uncertainty, inflation. Okay? So have a look at let me open this. So let's say we have 1, 2, 3, 4, 5. 5 variables I have. And I can describe these 5 variables. So x I have, and so I equal to 1, 2, 5. And so this should be distributed as I, D, I. So in the sense that I have a variable called uncertainty. So uncertainty, it's a variable at time t is distributed as say I, D, 1. It can be D1 equal to 1, D1 can be 0. Okay. Similarly, SP500 at time t, say ID2. Likewise, so we have say wage. So at time t is ID5. So I'm assuming that either D1 equal to D2 equal to D3, likewise equal to D5. Maybe the order of integration for all of them, at the most restrictive case, they can be equal. Or it is possible that D1 not equal to D2, not equal to D3, not equal to likewise, not equal to D5. So order of integration may also be different. So in this case, whenever we are assuming D equal to either 0 or D equal to 1, so this type of possibility may not arise. This type of possibility can arise only when we assume fractional degree of integration. So say that this is D1 equal to 0.4, say 0.5, this is 0.9, say for example 0.3. It can be different. But whenever we have 0 and 1, so I can say this is 1, 1, 0, 0, something like that. I have not tested it yet. You can test it and see the order of integration of those. How do you test the order of integration? Just look for the unit root test. You need to test if it is non-stationary, I1. If you find it's if you reject unit root, I0. So D equal to 0, D equal to 1. Okay. So in this case, I'm just trying to give a very generalistic idea. In the case whenever you have this type of presentation, so if xit, so in this case 5 variables, so xit, then the sum of all these a linear combination. What you see in this sum here is a linear combination. So alpha I xit, so linear combination of the different orders of integration of the variables should also be distributed as I maximum of Ti. So if the maximum order of integration is 1, so if I have 5 variables which are 0.2, 3, 4, what, and another is 1, so the maximum order of integration will be 1. Okay? So that's a theorem. So I did not invent it somebody, but there are some statistical proofs against in favor of it. Why? Can you give me some philosophical explanation? Let's say this gentleman, me, and 3 of us. So he is 0.4, 0.5, 0.7, 1, 0.8.
Because even if all you guys forgot that he slapped us, I'm still going to remember and go and punch him back.
The point is, philosophically speaking, if in a group of rational individuals, rational variables, there is a typical non-stationary variable. So it is more likely that the group may be affected more by the non-stationary chaotic behavior than by the
Rational behavior.
why is it so? Then I have to go back to some philosophies.
Craziness is more attractive.
Human mind, every person in the world, they always struggle or battle with two things, mind and conscience. Okay? We always, every point of time. Before coming here, I was thinking of telling a lot of good things. But then I thought, why to tell all those things? So I'm struggling, everything, to do or not to do. Conscience generally is very weak, but it wins at the end. Psychologists, especially Sigmund Freud, you might have heard his name, famous psychologist. So he was the first person to divide mental spheres like consciousness, superconsciousness, subconsciousness, etc. So he said that conscience is always weaker, but it always wins at the end, because at the end you will always know whatever I have done in my life, this might not occur. But mind is extremely powerful, lazy, always wants to do bad things. Okay? And so mind always wants to win against conscience. Just like in Indian philosophy, is like we have some stories, but apart from that, so it means even in Bible, in Quran, everywhere, you'll find exactly the same type of philosophy. Here, whenever there is a chaotic element within a group, so mind, because it is always lazy, wants to do always bad things, so it always wants to follow the non-stationary element. So that is the philosophy. And statistically speaking, we have also proved that if there is a series which is I1 and it affects the non-stationarity behavior, correlation matrix, ACF of whole series, and it is characterized by that one. Okay, so it's called group stability formation, group stability theorem. So Granger's group stability theorem, aggregation theorem, Granger's aggregation theorem, which says if in a group of economic or financial variables, if some of them are, say, ID1, 2, 3, 4, some of them are stationary and some of them are non-stationary. So the group behavior will be characterized by the non-stationary element.
Always?
Always. Okay? And we have also known philosophically why it is so. I will tend to always find the bad thing. That is always, it's more attractive, isn't it? And at least I know in different film industries, people, girls always tend to marry all that sort of big, you can, El Chapo, that Mexican guy, you know, his wife is a famous model, and so you know, all these girls always want to, I'm not blaming you, they always want to marry all the bad guys. They like that kind of idea. So that you can have the evidence. So why I'm trying to say, that is what, philosophical speaking, not many of them. Like that. Yes, so the idea is this. So that's the philosophical side, but statistically speaking, that's the Granger's aggregation theorem, which says this. What you find here, the sum of alpha I. So that gives you linear, that part is called combination. And then alpha is the coefficient of linear combination. So if I have three variables, okay? Say x1 and x2. So how do I make a linear combination? Have you, do you know this? Mathematically speaking, how can I form a linear combination of two variables? Think about a curve which is concave. Concave, you understand what is concave? Yes. What is concave? No, I'm not asking any statistical explanation. Give me what you understand when you see this type of graph, what it implies. Something is increasing at a decreasing rate. Okay? So, an example. I'm sure you will like this example.
Marginal utility.
I'm sorry? Yes. So, income and happiness. So, you know, whenever you have your income is rising, until a certain point, at this point, until this point, your happiness is increasing. More income, more money, more happiness. But then after a certain point of time, I don't want anything in the world. I just want a little bit of peace to survive.
More money, more problems.
And there is a very big theory behind it. And there is a very good example actually. In the UK, somebody owned this lottery, a couple of years, some £1 million. Then he was a banker, he left his job, he thought I have millions and millions of pounds. So he bought some big Jaguar, big cars, then houses and all those things. And one of his friends told him that, look, you have so much of money, let me also invest some money in my company. So he trusted him, he left his job and all those things, he was just lavish lifestyle he was maintaining. Then this friend invested some in the share market. Everything was gone after the financial crisis, everything gone. Now he doesn't have any job, anything. At some point of time, he said, I don't want any money, I just need some bit of this. There is a big economic theory behind
He
it.
didn't have any money.
Income and happiness. there are some
That's because of the lack of money.
have you heard about anything called, in the British Household Panel Survey, there is a specific question that we ask consumers, household people, that it is not your income that represents the national prosperity. It is your happiness. What we call life satisfaction. How satisfied you are with your life today, depending upon a host of factors. One of them is income, then health, your neighborhood, etc., etc. Different types of things. So today's national prosperity is actually championed by the King of Bhutan. King of Bhutan in 1970s, he was the first person to say national income is not important, real income is not important. But happiness. So in this case, say, income is increasing, happiness is increasing. But the structure of this curve, say at this point, this is your slope. At this point, the slope is decreasing, zero here, again, like that. Okay? At each point. So that type of curve, we can say this dy by dx equal to 0, d square y by dx square is negative. That is the second derivative of a concave curve. Whenever a curve is concave, so that second derivative means a rate of change of y, happiness, due to a small change in income. So it is negative. That means if happiness increases at a decreasing rate as income rises. Okay? Now I have 2 points, x1 here, x2 here. So then I can make a linear combination of these 2 points. So I can just say lambda amount of x1, 1 minus lambda amount of x2. So lambda can be 0 and 1 between. So 0.2 of x1, 0.3 of x2, like 0.7. So if it is 0.2, 1 minus 0.2, 0.8, like that. This is what we call linear combination. Okay? And then exactly the same thing here. Linear combination of variables. I can present linear combination as this one, or I can say present say x1 plus 2x2 equal to z. Some formula. So as long as it holds on linearity, no power term, any combination can be linear combination, plus, minus, anything. But if I say x1 plus 2x2 square equal to z, so that is not a linear combination. This is non-linear combination. That is what we don't know. But what this theorem says, any linear combination of ID variables. So you sum them, and that z is the indicator variable that represents linear combination of all non-stationary or stationary or integrated of order d variables. D can be different. Then this sys z means that system can be characterized by the highest value of the integration. So in my class today, I have 84 students present, and say 30% of them, very small amount, 20% of them are highly non-stationary, chaotic. They want to kill tapas at any instant, given a chance. And 70% of them, they love me. Okay, just like this gentleman, he likes me, always give some good example. See? So then I can say that ZT means 84 students. Characteristics is given by the non-stationary behavior. That is that. So we'll stop for 5 minutes, then I come back to the explaining the exact method of quantification.
You're accusing me of being the teacher's pet now.
See?
Okay. Alright.